All right, here's example number 4. Let's apply the derivative rules that we know. What do we know? 5 of them now, right? To help us find the derivative of all different types of functions. We have constant rule, power rule, we have that coefficient rule if we have a number in the front, and then we have the rule where if we have a whole bunch of different terms added or subtracted, we should be able to still take the derivative by just simply taking the derivative of each term separately. Let's apply those rules now. In example number 4, it asks us to find the derivative, and the first function is y equals 6x cubed plus 15x squared. You might notice that I have two terms being separated by a plus sign. I can use our rule then to be able to take the derivative of each term separately and then just add them together. So what would you say the derivative of 6x cubed is? Well, hopefully we've practiced using the power rule enough that we can quickly say that 6 times 3 is 18. If I subtract 1 to the exponent, I get 2. So the derivative of 6x cubed is 18x squared. So then what would be the derivative of 15x squared? Well, 2 times 15 is 30, and if I subtract 1, I get 30x to the first, or just 30x. So the derivative would be 18x squared plus 30x. All right, look at b. b looks a little more complicated, right? I can do the derivative of 12x to the fourth, but as soon as I see this radical, I know that I need to rewrite it. And on the last term, as soon as I see that variable in the denominator, I know that we don't know how to do derivatives of division problems, especially if there's a variable in the denominator. So we need to make sure that we rewrite all of these terms. Well, actually the last two, I guess, right? So pause the video, rewrite this problem so that it looks like a rule that we do know for each term. All right, when I rewrote this problem, I'm going to use good notation still. This is still original p of t is 12t to the fourth. I'm going to take the square root of t and really make it minus 6t to the 1/2. And in my last term, I'm going to bring that t up to the numerator and call it plus 5t to the -1. Now I can take the derivative of each piece separately using my power rule and that rule where we have a coefficient. Now I'm taking and finding the derivative. So you notice I've changed notation. I'm doing p prime now. The derivative of 12t to the fourth is really 48t cubed. The derivative of negative 6t to the 1/2 power, if I bring the 1/2 forward and I multiply it by 6, 6 times 1/2 is 3. If I subtract 1 from the exponent, my new exponent is t to the negative 1/2 power. On my last one, if I were to bring the -1 forward, that 5 turns into a -5. If I subtract 1 from the exponent, my new exponent is -2. All right, there's two things we want to do before our final answer. We want to make this t to the -1/2 a positive exponent and the t to the -2 a positive exponent. Leave the coefficients where they are and just make those exponents positive by dropping the piece down that has the negative exponent attached to it. So my final answer with positive exponents would be 48t cubed minus 3 over t to the 1/2 minus 5 over t squared. Ooh, that was a good one. All right, let's look at a few more. Ooh, look at C. C looks really complicated with not only a radical, what else do you notice? Do you also notice that there's a variable in a denominator? And we don't know how to do problems right now that have variables in the denominator. And unfortunately, you can't just take the derivative of all three pieces and call it good. I wish you could. That'd be way easier, right? But you can't. So as soon as we see that variable in that denominator and that radical, we have to think about how we can rewrite this problem into rules that we do know. We do not know how to do problems where we have variables in the denominator. One of my ideas is instead of taking this fraction that has a common denominator as one fraction combined, could I really rewrite this as two different fractions with the same denominator, right? Because if my problem looked like this originally, I could actually make it look like this by adding the numerators and combining that common denominator. So if I can write it like this, then I can use that rule backwards and write it as two separate denominators. Now, how does that help? Well, it looks a little more complicated, not less complicated, right? Well, actually, you should be able to see now that I can take each one of these terms and reduce them. Can't I reduce an x from the top and an x from the bottom of each of these terms? When I do that, x cubed divided by x is really just x squared. When I reduce a half of an x, really, on the top and the bottom, I end up with a half of an x, not really a half of an x. I should really be using correct terms here. But if you think about reducing x to the 1/2 on top and an x to the 1/2 on bottom, in that second term, I'm left with a 3 in my numerator and an x to the 1/2 in my denominator. I like the x squared, but I don't think I quite like the 3 over x to the 1/2 yet, because I still have a variable in my denominator. But can I take that x to the 1/2 now and bring it up to the numerator? So now I have two terms that are separated by a plus or a minus sign, where I can take the derivative of x squared, and now I can take the derivative of 3x to the negative 1/2, because now I don't have any more variables in my denominator. So I had to do a lot of manipulation first on this one in order to get it to look like it is now before I can even start to take the derivative. So practice a few of those problems to make sure that you can rewrite it into rules that we do know. Be careful, you can't just take the derivative of the top and the derivative of the bottom and call it good. We don't know how to do that yet. All right, now that they're separated by a plus sign, I should be able to take the derivative of x squared, which is just 2x, and I should be able to take the derivative of 3x to the negative 1/2 by bringing that negative 1/2 forward, subtracting 1 from my exponent. I'm looking at this and thinking that I did something wrong. Did you notice? Isn't my exponent supposed to be a negative 3/2, and I have a 1/2 here? So let me change that. See, we all make mistakes. Be careful. If I bring my negative 1/2 forward, I have a negative 3/2, and then I have x to the negative 3/2, which needs to come down and become positive. All right, that looks better. Okay. Whew, see, be careful. Lots of different ways to make mistakes, so you got to be really careful on all of these. All right, last one. In example number 4, look at D with me. D looks a little bit different than what we're used to as well. We have this binomial, something with two terms, and it's raised to the second power. Unfortunately, you cannot use the power rule, try to bring that exponent forward, subtract 1 from the exponent, and call that the derivative, because this isn't quite in power rule form. Remember, power rule is only an x to a certain exponent, and this has way more than just an x to the second power, right? And so right now, we don't know how to solve or take the derivative of this problem the way it is. So how can we rewrite this problem, the 4x squared minus 3x squared, so it looks like a form that we do have a rule for? Well, maybe you've noticed that taking something and squaring it really means you have two of them that you're going to multiply. So 4x squared minus 3x squared really means that I have a 4x squared minus 3x times another 4x squared minus 3x. And then can't we FOIL? So if I FOIL and combine my like terms, you might want to pause the video and do that real quick, you end up getting a 16x to the 4th minus 24x cubed plus 9x squared. And now I have three separate terms separated by plus or minus signs. All my variables are up in the numerator, and I should be able to use the rules that I do know to find the derivative of each term separately. But I had to do a little bit of work before I could get there. I can take the derivative now, and the derivative of 16x to the 4th is really 64x cubed. The derivative of 24x cubed is my minus 72x squared, and the derivative of 9x squared is really 18x. So I can find the derivative. I just have to do a little bit of work on all of these to make them look like problems we do have rules for. So you might need to rewrite your problem first before you can even find the derivative. So practice doing all sorts of problems like that, because every problem is going to look just a little bit different. Make sure you can rewrite it into a form that we do have a rule for, and then be able to apply those rules.